Today we are doing integrals involving powers of trig functions. This topic is not covered on the calculus AP exam, but it definitely will be on my test, and your Calc 3 professors will think that you know how to handle integrals that have powers of trig functions in them. Before I get started, we know that when there's a product of two functions in the integrand, you cannot just integrate each individually and multiply those two antiderivatives together. It does not work that way, all right? And we know that. We should know that. But for some reason, with trig functions, kids want to do that. They want to, when you see things like sine x, let's say, times tangent x, that's a bad example, but whatever. When you see something like that, kids want to just take the antiderivative of sine and multiply it by the antiderivative of tangent and be done. And you cannot do that, all right? Can't do it that way. You have to do something else. We have to use our identities or somehow manipulate to get it into something that we can find the antiderivative of. Now, before I go on, if this was a plus or a minus instead of a multiply, yes, you can do that. We do it all the time, but not when there's a times or a divide. You cannot do that. Another thing kids like to do here, let's say that we have sine to the 5th x dx. It's a power of a trig function. Do not use the power rule with that. Do not use the power rule. The power rule says if you have x to a numerical power, then yes, you can use the power rule. You raise the power by 1, you divide by your new power, and you're done. That does not work if this is not an x. If it is a function, it does not work unless you can u-sub that function. If you can u-sub it and get it into something like u to the 5th du, then yes, you use the power rule. That'll be u to the 6th over 6 plus c. But it only can happen if you can do a u-sub with it and get the correct du out of it. All right. We need to know all of our basic trig derivatives and antiderivatives. We need to know those. All right, everything that you're looking at right here, you just have to know those. In class on this day, I always do pull out some flashcards on these, and as you're walking in the door, we'll give you guys some flashcards. Other identities to recall. The Pythagorean identities, we need to know those. Sine squared x plus cosine squared x is equal to 1. And if you divide both sides of this by cosine squared, you will get tangent squared plus 1 is equal to secant squared. If you divide both sides of this by a sine squared instead, you'll get 1 plus cotangent squared is equal to cosecant squared. Okay, so we need to know those, so that we can manipulate that integrand sometimes and get it into something that we can integrate, that we know the antiderivative of. Let's review the double angle identities. Here is the double angle identity for sine of 2x. It's been a long time since we've done that. It's been about a year since you saw that in pre-cal. Okay, this one is used, but not as much as this one for us. And I'll tell you why. It's because we often have integrals with either a cosine squared x or a sine squared x in them. So we need to write this. We can't use the power rule, right? We need to write this in some other form. And if you take this, if we use, in fact, let me do it on one of these. Here's our cosine of 2x is cosine squared x minus sine squared x. If I take this And if I replace sine squared x, by 1 minus cosine squared x, then I will have cosine of 2x is cosine squared x minus 1 minus a negative cosine squared x, so that'll be a plus a cosine squared x. That means that we have 2 cosine squared x plus 1 over there. I'm sorry, minus 1 over there. I'm going to add the 1 to the other side. I'm going to solve it for cosine squared. I'm solving this for cosine squared. So I have a 1 plus cosine of 2x is 2 cosine squared x. Now divide both sides by 2. And we get that cosine squared x is equal to 1/2 plus 1/2 cosine of 2x. If instead of replacing sine squared x with 1 minus cosine squared x, if we replaced cosine squared x, with 1 minus sine squared x, if we did that, then we would get to this form of that identity. These are the useful forms here. That's why I put a little star in there. I don't know why that's not wanting to, okay. So, common mistakes I see kids make. When they have a sine squared, they want for this to be a sine, and it is not. It did not come from the sine of 2x identity. It came from the cosine of 2x identity. So both of these get a cosine of 2x. The cosine squared ends up with a plus between the two terms. The sine squared x ends up with a minus between the two terms. I didn't show you that work, but you can imagine how that would happen because we're going to have a negative sine squared over negative 2 sine squared x over there. Anyway, okay, another thing to note here, whatever angle is here must be doubled over here. Whatever angle is there must be doubled over here. So if you have cosine squared of 9x, then we can change that to 1/2 plus 1/2 cosine of 18x. All right? And then clearly this is very easy to integrate because we know our antiderivatives. Okay? All right, let's go on. Let's dive into some examples. So in this first example, get another color here. In this first example, we are going to do a u sub. Remember back when we first started u sub, we let u be whatever was being raised to the power, right? That's what we did. Or what was underneath the radical. So I'm going to let u be cosine of 3x. So du is negative 3 sine of 3x dx. I'm going to divide both sides by that negative 3, and I get that negative 1/3 du is sine of 3x dx. So in place of this sine of 3x dx, I'm going to be putting negative 1/3 du. In place of cosine to the 6th 3x, I'm replacing it with u to the 6th. So we can rewrite this integral as negative 1/3 integral u to the 6th du, and now we can use the power rule. We did a u sub, now power rule, okay? So negative 1/3 times 1/7 u to the 7th plus c. That would be a safe spot if it was an FRQ. As a multiple choice answer, negative 1/21 cosine to the 7th of 3x plus c. Before I leave this problem, look at what we did here. We saw that there was a single sine of 3x here, a single. And then we had cosine being raised to the 6th. This, from the get-go, was going to be our du, or part of the du. Okay? A tip. I cannot say always, but I can say almost always. Almost always. Let u be a single trig function. If you're going to do a u sub with a trig function, almost always let u be a single trig function, not a power of a trig function, a single trig function. Okay? So I did not let u be cosine to the 6th of 3x. Let u be a single cosine. If you let u be a cosine of it to the 6th, you're going to have to do the chain rule. And you would get 6 cosine to the 5th 3x times a negative sine of 3x times that 3. You don't want that. You don't want that to be your du. So let u be a single trig function. Okay, number 2. Whenever you see a sine squared by itself or a cosine squared by itself, use the identity with the 1/2. If it's by itself, the identity with the 1/2. So this is going to be 1/2 minus 1/2 cosine of double the angle dx. So that will be 1/2 x. Integrating cosine, keep the sine. Integrating cosine, keep the sine. We're going to have to divide by the 10. We're doing a u sub in our heads here. Divide by the 10, get 1 over 20 sine of 10x plus c, and we're done. For number 3, 1/2 plus 1/2 cosine of double the angle dx. So 1/2 x, integrating cosine, keep the sine, 1 over 16 sine of 8x plus c, and we're done. So sine squared or cosine squared by itself, that's what you do. You guys, in our next unit, we're going to be finding areas inside of polar curves. Inside of polar curves. Remember polars, we would have things like r is equal to, let's say, 3 cosine of 4x, of 4 theta. That would be an 8-petaled rose, each petal length 3. The formula, we'll find out, I'll show you why this is the formula for it, for the area inside the polar curve will involve 1/2 r squared d theta. Many of our r's have either a cosine or a sine in them, so when you square it, you're going to get a cosine squared. You're going to be doing things like that. So this identity is very useful because of that. All right? Very useful. Okay, number 4. Okay, so what to do? We could change it all to sines and cosines. We could use an identity, because as soon as I see a cotangent squared, I know that I could use the identity that says cotangent squared plus 1 is cosecant squared. That's one of those Pythagorean identities. So you can use an identity, change sines and cosines, move cosecant to the top, make it a sine. We can do lots of things. My best advice is do something and see what happens. I think since I wrote this down, I'm going to go ahead and use this and see what happens. So in place of cotangent squared, I'm going to replace it with cosecant squared x minus 1. And now that I did that, I like what I'm seeing because I have a single term in the denominator, I have an STD in the denominator, yeah? So I'm going to quickie divide this. I can quickie divide this, make it 2 terms. And I can already see what's going to happen here. I like what I'm seeing. Cosecant squared x divided by cosecant x. Cosecant x minus 1 over cosecant x, that's sine of x. And as soon as you get a single trig function, we need to know those antiderivatives. The antiderivative of cosecant is negative ln absolute value cosecant x plus cotangent x. The antiderivative of sine, change the sign, and it's cosine. So that worked out very nicely using this Pythagorean identity. It would have also worked if we had changed it to sines and cosines, and done, we would have ended up using that Pythagorean identity, probably, I'm guessing. All right, number 5. Number 5. When I look at number 5, what I see is I see a function and I see its derivative. So I know exactly what I'm going to do here. I'm going to u sub that function because its derivative is sitting there like a Christmas present from Santa Claus. Okay? So u will be tangent x, du is secant squared x dx, exactly what's written here. That's du and that's u. I really don't even have to bother rewriting this integral. It would be integral u du. So that is 1/2 u squared plus c. That would be a safe stop as long as you have said what u is. If you didn't say what u is, then you just go back to tangent at the end. So 1/2 tangent squared x plus c. Okay? By the way, if we took the derivative of this, let's take the derivative of this. We're taking the derivative of 1/2 tangent x squared plus c. That will be, we got a chain rule, 2 times 1/2 is 1. Keep your tangent, reduce the power by 1, and multiply by the derivative of tangent. It's exactly what we had there. Okay? All right, number 6. Cosine cubed x, sine cubed x. All righty, what to do here? In class, I let the kids take a couple of minutes to brainstorm, see what they would do. Several people said just u sub something, and I said, okay, let's u sub something. Let's u sub a single, not a power, right? Not a power, a single sine x, and see what we get. If we u sub sine x, then we're looking at a u cubed right here. So du would be cosine x dx. I do have a cosine x dx. In fact, I have 3 of them, 2 more than I want. So what do we have if we do this u sub? I'm going to take one of those cosines and put it back here with a dx. I'll still be left with 2 cosines though. Cosine squared x, sine cubed x, a cosine x dx. Here's my du. Here is a u cubed. This is a problem because when you u sub, you have to have all u's. All u's. And I still have an x. That's a problem. Can we change this to have signs in it? Yes, we can. That is 1 minus sine squared x using the Pythagorean identity. Sine squared x plus cosine squared x is 1. Using that identity, we can do that. Now this is 1 minus u squared. So our integral has become 1 minus u squared in parentheses, because we're going to have to distribute here, u cubed du, all u's. As soon as we get all u's, now let's distribute and finish things up here. U cubed minus u to the 5th du. 1/4 u to the 4th minus 1/6 u to the 6th plus c. A multiple choice answer, they would go back to having sine x in here. 1/4 sine to the 4th x minus 1/6 sine to the 6th x plus c. Okay? By the way, if instead of letting u be sine x, we let u be cosine x, that would have worked out very similarly. The only difference is when we're taking du, we would have a negative sine x. So in the end, it would be negative 1/4 cosine to the 4th plus 1/6 cosine to the 6th plus c. And those two are vertical shifts of each other. They have different c's, but it's the same shape. Okay? So sometimes when you do one of these, your answer might look different from my answer, but it might be equally correct. Number 7. Number 7. Okay, again, in class I let kids brainstorm a little bit. Most said let u be a secant of 3x. So let's let u be a secant of 3x. If we do that, then du is 3 secant 3x tangent 3x dx. Okay? We do have the tangent 3x. Do we have a secant 3x? If we pull 1 from these 5, we can put it over here to be our du, right? So I can rewrite this as secant to the 4th of 3x times secant 3x tangent 3x dx. And now I have to remember that I have a 3 there. I'm going to divide by that 3 and put it with the du. In place of that, I am putting 1/3 du. In place of this, I'm putting u to the 4th. Okay? So we will have as an integral 1/3 the integral of u to the 4th du. That is 1/3 times 1/5 u to the 5th plus c. As a multiple, that would be a safe stop spot. That's our first safe stop spot. As a multiple choice answer, they would have 1/15 secant to the 5th of 3x plus c. And again, you guys, if we took the derivative of this, we would be using the chain rule like we did up here. We would get that. Okay? All right, number 8. Secant to the 4th x. So I let kids brainstorm, and they brainstormed for a few minutes on this one. And then they came to the conclusion that we should rewrite this as secant squared x times secant squared x, and use the Pythagorean theorem involving tangent squared x. The Pythagorean identity says tangent squared x plus 1 is secant squared x. So I can replace one of these secant squared x's with tangent squared x plus 1. And I will get tangent squared x plus 1 times secant squared x dx. We like that because if I let u be tangent, its derivative is there. So I'm going to let u be a single tangent, not tangent squared x plus 1, a single tangent, a single trig function. Okay? And then du will be secant squared x dx, and we can replace the secant squared x dx with du, and we are replacing tangent squared x plus 1 with u squared plus 1. So our integral has become u squared plus 1 du. So 1/3 u cubed plus, be careful right here, the integral of 1 du is u, not x. All right, be careful with that. That would be a safe stop spot because we named what u was as a multiple choice. 1/3 tangent cubed x plus tangent x plus c. And once again, you guys, if we take the derivative of this, we would get that. All right, number 9. What to do, what to do. I'll let kids think about this one. Most said, let's bring these to the top. Let's get it out of the denominator. So I said, okay, we can do that. That's a legal math move. If we bring cosecant to the top, it's sine x. If we bring cotangent to the top, it's tangent x. And then they said, let's change tangent x to sine x over cosine x. And I said, yep, that is also a legal math move. Oops, cosine x. So when we multiply these two together, we get sine squared x over cosine x dx. And then somebody in class, in each class period, said, let's use the Pythagorean theorem on, I keep saying theorem, the Pythagorean identity on that sine squared. So sine squared x plus cosine squared x is 1. So sine squared x is 1 minus cosine squared x. And now, like we did earlier in this problem set, now we have a single term in the denominator, an STD, and we can split it up. Split up the numerator. So 1 over cosine x is secant x, minus cosine squared x over cosine x, cosine x. And we know the antiderivative of each of those. ln absolute value secant x plus tangent x. If you're integrating cosine, keep the sine. And we're done. A little bit more involved one there. Lastly, here we have this one as an example. In every class, I was very pleased because in every class, kids said, let u be the sine of 2x. And I asked why, and they said because it is under a radical. And I said that is correct. So let's start there, and if we need to change, we change. So if u is sine of 2x, then du is 2 cosine of 2x dx. I do have a cosine of 2x. In fact, I have 3 of them. So I'm going to take 1 and put it back here with the dx. I'm leaving the other 2. Forgot my little radical there. So cosine of 2x dx right there. So that's good. I'm going to save that because it's right here. Yeah. That's going to be my 1/2 du eventually. Okay. I do have u to the 1/2 right here. And then I have the x's still. So I need to get rid of my cosine and make it a sine. And we can do that using that Pythagorean identity. I can replace cosine squared with 1 minus sine squared. Keep your 2x. And that will be 1 minus u squared. So my integral has become 1 minus u squared, u to the 1/2, times 1/2, I'm going to take out the 1/2, du. Distribute. U to the 1/2 times 1 minus u to the 1/2 times u squared. We add the powers, u to the 5/2. So that is 1/2 times, add 1 to your power, divide by your new power, add 1 to your power, divide by your new power, plus c. And for a multiple choice answer, we can mess with this. 1/2 times 2/3 is 1/3. I might write this as sine of 2x to the 3/2 power, and then this would be a minus 1/7 sine of 2x to the 7/2 power plus c, and we're done. So guys, the only way to get even vaguely comfortable with integrating powers of trig functions is to integrate powers of trig functions. So you just have to go and do it. All right? So practice, practice, practice. Remember, you guys, that this topic is not covered on the AP exam, but it will be on my unit test, and it is very, very eligible for the integration bee. All righty.